Hello, today we continue with our A-level physics revision series looking at Hooke's law and Young's modulus. Hooke's law applies to anything that can be stretched but which will then return to its original position, like this elastic band. It doesn't apply to anything that can be stretched but which then doesn't return to its original position, like this blue tack. This is known as elastic. This is known as plastic. It just doesn't go back again. Where you have a piece of material, let's say it's a piece of elastic, and you stretch it by an amount x, that's the stretch of the elastic, we say that the force that you have to apply on that piece of elastic, we'll assume that this end has been pinned, so it's fixed. The force you have to apply to this end to stretch it to that is proportional to the extension. And that is in essence what's called Hooke's law. And whenever you have a proportionality, you can always write that as that the force equals some constant times x, where k is what's called the spring constant, or sometimes it's called the stiffness constant. And it doesn't only apply to elastic, it can apply, for example, to wire, or, as we shall see, to springs. If you take a spring and put a mass m on the end, that mass will exert a force mg, where g is the gravitational attraction. And what will happen is that that mass will go down to a new position here. It will go down by a distance x. And once again, the force is equal to k times x, where k is the spring constant. It relates specifically to that spring. The greater the force, the greater the extension. And this means you can use a spring to measure the weight of something. The weight, of course, is the mass times the gravitational attraction. If you put a weight of a certain amount on the spring, it will go down by a certain distance x. If you put double the weight on the spring, it will go down 2x. So you can measure the weight. Notice it's always the weight. The weight of something on Earth will be different from the weight on the moon, because gravity is different on the moon. If you want to measure comparable masses, you have to do that by using balancing scales. And then you can measure the mass in one scale versus predefined, as it were, masses in the other. But a spring balance will measure weight. If you were to perform an experiment where you took the same spring but put different masses on the spring and measured the extension x that each mass gave, then you could plot the force, which of course equals the mass times the gravitational attraction, and gravity won't change as long as you don't change your position, and you plot that against the extension f, and what you find, of course, is that you get a straight line, and the gradient of that line will be k, because f equals kx. And that is Hooke's law. But you can't keep doing this indefinitely. Sooner or later, if this is elastic, the elastic will break, or if it's a spring, the spring will become deformed, and what you find is that the curve changes. And so only in this region have you got Hooke's law. Once you get beyond the point at which the spring deforms or the elastic breaks, you're no longer in Hooke's law region. And this point here is called the elastic limit. It's the point at which the spring or the elastic or whatever does not return to its original position. When the spring once stretched will return to its original position once you take the mass off, we call that elastic. Once you get beyond that point where the spring is permanently deformed, then we call that the plastic position. What is actually happening within the spring or the elastic or whatever it may be is that there are atoms. Those atoms are joined together by atomic bonding. Now if you stretch them a certain amount, they have all got a little bit of give. They can stretch out the atoms without any problem. And when you release the material, the atoms will cheerfully go back into their original place. But if you stretch the material too much, either what will happen is that the bonds will break and therefore the actual material will break and the elastic band will actually snap in half, or the atoms will become set in their new way and the spring or the elastic or the wire becomes permanently deformed. It no longer returns to its original position. Hooke's law can work not only by extending a spring, but also by compressing it. If you have the capability of fixing the spring at this end, you might put a force on pushing it inwards, and there will then be a reduction in the length of the spring by a distance x. And once again, the Hooke's law formula F equals kx applies. We're now going to look at stress and strain. Stress, or sometimes called tensile stress, is equal to the force divided by the area. So if we were to take, for example, a wire whose cross-sectional area of the wire was A, and you apply a force to that wire. Typically, if we draw the diagram, here's the wire. It's usually quite a thin wire, and on the end of it we have a mass m, and of course the force acting down will therefore be mg. Well, the force divided by the area will be the stress, or the tensile stress, put on that wire. What are the units? Well, force of course is measured in newtons, area is measured in meters squared, so normally you would say that stress is newtons per metre squared. But in fact we have a new name for that. It's effectively pressure, and it's measured in pascals. Tensile strain, or strain by contrast, is the change in length compared to the original length. So if you have a wire, and that's of length L, and you extend it by a distance x by applying a force, then the tensile strain, or the strain, is equal to the extension divided by the original length. And that has no units, because this is measured in length and this is measured in length, and the length divided by length just gives you a number with no units. And stress and strain can be measured whether you are extending a piece of wire or compressing a spring. And once again, you can perform an experiment where you take a piece of wire, you put a mass on the end of it so that the force is mg. You measure the cross-sectional area carefully so you know what the cross-sectional area is, and you put different masses on the spring and measure the extension that you get. You also of course measure the original length of the wire, and we know that the stress is force over area. Well, force is simply the mass times the gravitational attraction and the area you measured. Strain is x, the extension, divided by L, the original length of the wire, both of which you can measure. And that means you can now plot a graph of stress against strain. And what you'll find is that you will get a straight line, and that's a Hooke's law consequence. But eventually, of course, what will happen is that the material, the wire, will no longer return to its original position. It will become permanently deformed, and so you'll get a graph that looks like that. And depending on the material that you're using, the material will either break, and there will therefore be no further extension, or it will go into the kind of plastic mode where it no longer returns to its original position, or sometimes it can get into a position whereby it will just continue to extend even though you're not putting any further mass on it. What is the work done when we extend a piece of elastic or a spring? Let's take a piece of elastic, it could be a spring, original length L. We apply a force, F, and we get an extension of X. What is the work done to move or to extend this? Remember, that end is fixed, this end is being extended. What is the work? Well, the work is the force times the distance. But remember that the force is not constant, because force equals kx. That's Hooke's law. So as you begin to extend the elastic, you will need to put an ever greater force to get it to stretch, because the greater x, the greater the force. So the average force that you use to go over a distance of x, the average force is equal to this force divided by 2. Because it goes from 0 to the full amount of the force that you need to achieve this extension. Capital F is the force needed to achieve an extension of x, but you don't need to apply that force through the whole of the extension. The force you apply goes from 0 here to F here, and the average is F over 2. So the work done actually is F over 2 times x. But F is kx, so that simply becomes kx squared over 2. And that is not only the work done to stretch the elastic from this point to this point, it's also the potential energy that is now bound up in that elastic. If you hold the elastic at this point and let go, it will spring back and it will give off energy. And that energy is kx squared over 2. So when you pull out a piece of elastic, you give it potential energy. You have to hold it there, because if you let go, it will fling back, spring back even. And the energy that it gives off is the potential energy, which is the same as the work done to pull it out in the first place. And that's kx squared over 2. We now come to Young's modulus. Young's modulus, which is usually represented with the capital E, is equal to stress divided by strain. Stress over strain. Stress, or tensile stress, you'll remember, is force over area. Strain is the extension divided by the original length. And if you work that out, that becomes force times length divided by extension times area. And you might also note that force times length is a measure of work done. Force going through a particular distance is a measure of the work or the energy. Extension times cross-sectional area is volume. So really, Young's modulus is measuring the work done or the energy stored per unit volume of the material that you are stretching. And again, you can do an experiment to measure Young's modulus. Take a wire, put varying masses on the wire and measure the extension x for each mass. The force, of course, will always be mg. The original length of the wire, as long as you don't deform it, is going to be L, and you can measure the cross-sectional area of the wire carefully. And then you can do a series of experiments where you measure for different values of mass, you measure the extension, so you're simply getting a series of mass versus extension readings, and from that you can calculate the stress, which is force over area. The force will be mg, that will change every time you change the mass. The area is the area of the wire, that won't change. X is the extension depending on the mass that you put on, L is the original length of the wire, which won't change provided it doesn't get deformed. So you can calculate for each of these values of mass and consequent extension, you can calculate the stress and the strain. You can plot a graph of stress against strain, and you will get a straight line, and the gradient is stress divided by strain, which of course is Young's modulus. And for any given extension of the cable, let's say that the stress, force over area, strain, extension over original length, the energy contained, the potential energy contained in the stretched material is the area of that graph. And the area of that graph, of course, is simply the area of a triangle, which is half the base times the height. So that is half the stress times the strain. And that's the same as we had before when we calculated the energy or work done. It was half of kx squared. And here the same principle applies. The energy stored in the stretched material, which would be released if you let it go, is half the stress times the strain. Some constant times x, where k is what's called the spring constant, or sometimes it's called the stiffness constant. And it doesn't only apply to elastic, it can apply, for example, to wire, or, as we shall see, to springs. If you take a spring and put a stick, we say that the force that you have to apply on that piece of elastic, we'll assume that this end has been pinned, so it's fixed. The force you have to apply to this end to stretch it to that is proportional to the extension. And that is in essence what's called Hooke's law. And whenever you have a proportionality, you can always write that as that the force equals position, like this blue tack. This is known as elastic. This is known as plastic. It just doesn't go back again. Where you have a piece of material, let's say it's a piece of elastic, and you stretch it by an amount x, that's the stretch of the elastic. The mass m on the end, that mass will exert a force mg, where g is the gravitational attraction. And what will happen is that that mass will go down to a new position here. It will go down by a distance x. And once again, the force is equal to k times x. Hello, today we continue with our A-level physics revision series looking at Hooke's law and Young's modulus. Hooke's law applies to anything that can be stretched but which will then return to its original position, like this elastic band. It doesn't apply to anything that can be stretched but which then doesn't return to its original position.